Hello Science Alliance, I'm Lara, this is Set of Science. I'm streaming free live IGCSE physics lessons just into the internet because that is what I have, well, I trained to teach physics. I didn't train to do this, but I've learned how to do this over 6 years. If you are enjoying the fact that a fully qualified physics teacher with a first class science degree is streaming lessons for free, you can pay me for it at the end. This is literally my full-time job. I know. Let's get started because probably a lot of you aren't new. We've done 2 lessons on magnetism already. If you have done those lessons with me, I would sort of hope that you'd be able to answer these questions. I tried to be like an evil exam question because I reckon you've spent ages and ages, right? You're about to do an exam, you've revised magnetic materials. This is just the kind of trick that an exam would pull. Which of these materials would not be attracted to a magnet? You've suddenly got to sort of do the opposite of what you thought that you had to do. Which of these materials would not be attracted to a magnet? It's copper and aluminium, because you had to remember that magnetic materials, the things that would stick to a magnet, are iron and steel and cobalt and nickel. I mean, steel's a bit of a cheat. That's just because it's got iron in it. It's iron with usually a little bit of carbon in it. But yeah, all of those materials would be attracted to a magnet. Which is usually found in the core of electromagnets. And why? Well, you had to remember what we were talking about last week, about hard materials and soft, like magnetic materials. So the thing usually found in the core of electromagnets is iron. Why is that? Do you remember like what the whole point of an electromagnet is? What are electromagnets supposed to do? We looked at a picture of a massive electromagnet on a sort of crane type thing, and its job is to pick up cars in scrapyards, move them around, and then dump them somewhere else. You can only do that if you can turn the magnet on and off again, can't you? Well, I'm not going to do that thing where I tell you and then I show you the PowerPoint. I worked hard on this PowerPoint. I'll just show you the PowerPoint. It'll help you understanding much more than my words, I think. Magnets have magnetic fields around them, yeah? You remember that? That's how they feel other magnets without touching them. They're surrounded by these invisible force fields. It's important for this lesson that we remember the magnetic field lines always move from the north to the south. You gotta think people from north going down to London to see Les Mis and drink 14-pound glasses of wine. That's the way the country works. So magnetic field lines do the same. Go from the north to the south. So the particles inside, iron and nickel and cobalt, they are like teeny tiny little magnets, okay? That you can sort of think of the atoms as being like tiny magnets. Usually we've discussed this, they're all facing in different directions, so you don't really notice it. But if you put a magnet near these materials, so you put them into a magnetic field, then all those little magnets line up just like compasses do, and we say that the material has become magnetic, okay? Because now we've got a sort of, like all the magnets kind of add together, if you like. Now it's magnetic, see? So hard magnetic materials are very difficult to unmagnetize once this has happened. If you've got any magnets in your house, they will probably be made out of a hard magnetic material. They've been magnetized. The whole point is that they're magnets, so that you want to be able to take the magnetic field away and they stay magnets. Soft magnetic materials lose their magnetism once the magnetic field goes away. I showed you last week the weird activity where you can put paper clips together with a magnet and then take the paper clips off and they stay together, but iron nails don't stay together because iron is a soft magnetic material. So as soon as the magnetic field disappears, iron goes back to not being magnetic, which is great for electromagnets, right? Okay, sorry, but this recap sort of feels important. Last week we talked about how moving charged particles, like that's what electricity is, right? It's just particles that are charged moving through a wire. They generate magnetic fields. If you're like me, this is a very simple sentence, but really hard to get into your brain. I find all this stuff quite confusing because magnetism and electricity, we're talking about stuff that you can't really see. I mean, who even knows what a charged particle is, right? You've got positive and negative particles. When they move, they make magnetic fields. They've got to be moving. Just a proton, just very still, that isn't generating a magnetic field. But charged particles, positive and negative particles, when they move, then you get magnetic fields. Is that right? Okay, I'm gonna move on. Oh look, I did a cool PowerPoint special effect. Here you go. just in case you're struggling to understand. Compass, not moving. As soon as we turn the hairdryer on, electricity flowing through wire, oh, compass starts to move. Yeah. Okay, so this led us last week to this sort of discovery. Moving charged particles, so electricity flowing through a wire, creates this magnetic field. So if you get loads of wire and you coil it up and you run electricity through it, you've got a magnet. Is that okay? And it's an electromagnet. It's one that you can turn on and off. When the current is flowing, lots of charged particles moving, because what is a wire? A coil, it's just wire really close together. Loads of charged particles moving, big magnetic field, cool electromagnet. As soon as you disconnect the power supply and there's no current flowing, the magnetic field goes away, you haven't got a magnet. Awesome. Okay, so there are 3 ways. At the moment, you're just looking at a big piece of coiled wire on the screen. It's an electromagnet. There are 3 ways to make that electromagnet stronger. Can you have a think, please, about what they are? And we better start our craft while you're doing that. 3 ways to make the electromagnet stronger. I said to bring a box with you, like any kind of box really. What I'd like to do, and the jury's kind of still out on how useful this will be, is I'd like us to make a kind of cardboard egg whisk type thing. Make a small box and put the egg whisk inside the small box, like that, okay? So first of all, I just want you to cut down a box, and then we'll make the egg whisk thing that we can put inside it. All right, you got that? And with the egg whisk has got quite a long stick, so that we can poke a hole in the box and stick it through. I'm just going to keep saying that even though I can't hear your response. Is that right? Yeah? Is that okay? So I'm going small this time. I've made a big one yesterday. I'm going to go small and cute. I've got this box of breadsticks, and I'm going to chop the box so that it's about, I've got about a third box that I need. Yeah, chop a third off, and then we'll use that third for making the egg whisk. So there you go. Right, 3 ways you can make an electromagnet stronger. I reckon one of them, hopefully, if you came to last week's lesson, you've got straight away. Because you might have even been looking at the picture thinking, Larry, you haven't finished off your electromagnet. There's something missing. We just talked about it. What is it? There we go. Done my third. One of the things you can do is add an iron core. Remember, it's got to be iron because it has to stop being magnetic when you turn the electricity supply off. Let's put one in. Oh, there you go. Looks better, doesn't it? So you add an iron core because then you've got the magnetic field of the iron core as well as the magnetic field of the wire. Can you think of 2 other things that we could do? It's quite hard this. Someone made a comment yesterday which sort of just ended up doing 2 in 1, like said one thing that kind of covered both of them. 2 other things you could do to make that electromagnet stronger. And if you think you've got them, think very carefully about your wording. Think about the really annoying examiner marking your IGCSE physics paper. He's going to be like, oh, well, I didn't know exactly what you meant, so you didn't get the mark. It's not their fault. It's their job to do that. Okay, so the first one is you could add more turns. Did you say add more wire? I know, right? You can't say add more wire. You can add more turns. Why can't I just say add more wire? Here's a cool PowerPoint special effect explaining how. I can't say add more wire because I could look at what I've done here. I've added more wire, right? I've just done a really long bit of wire coming off the end of the electromagnet. I've added more wire, but that is not going to make this electric field, this magnetic field stronger, right? So you've got to be really careful with your language if you're going to get marks. Add more turns. Don't say add more coils, because this whole thing is a coil. Add more turns. It's just a memory game at this point, because, yeah, this bit of wire isn't technically making this electromagnet stronger. And the other thing is increase the current. If you said increase the voltage, then well done. Oops, wait. Oh, it just opened up like the calendar on my phone or something. There we go. If you said increase the voltage, well done, but forget about that now, please. And remember, increase the voltage. What someone said yesterday on Facebook was, increase the charges, which I thought was smart because that sort of covers 2 in 1, right? If you're putting more turns on, then you've got more charges kind of packed into that small space. So that would increase the magnetic field. Or if you increase the current, if you did the electricity lessons, you might remember that current is the amount of charge per second. So if the current is higher, you got more, like they're flowing around faster, so you also get a stronger magnetic field then as well. Okay, I'm going to ask you some quick questions about an electromagnet that I made, but we better start making our egg whisk. So what I would like from you, please, where's the one that I made as a practice? You basically need to make something this shape, but I think I would make the stick a bit longer. So you need like a rectangle on a stick. We're just going to make a rectangle on a stick first of all. And it's got to fit inside this box. So my box is quite narrow. So I've got to do quite a thin rectangle on a stick. Here we go. Yeah, I've made an electromagnet. Right, come on, Lara, it's not that hard. Okay, I'm just going to cut a piece of cardboard, cut a cardboard rectangle that is slightly narrower than my box. That we don't really want it to touch the sides, so I'm going to make this cardboard rectangle slightly smaller. Yeah, that's okay. Maybe I'll make it a tiny bit smaller. You don't want it to be touching the sides of the box, ideally. There we go. So when you've got a piece of cardboard that fits inside the box, you can turn that into a rectangle on a stick. Okay, so I was trying to make a electromagnet, right? Get a piece of metal, coil some wire around it, and use it to pick stuff up. There we go. Are you okay? You just make a rectangle on a stick, make a little lollipop type thing. And it's got to fit into your box like that. The stick can be quite long because we'll poke a hole in the box and we'll stick it in like that. Do you get me? If you're way ahead, yeah, then you can make 2 of those. Right, so here's my electromagnet. It's a bit rough and ready, but I think it does the job. I got a chisel, a steel chisel, and I turned loads and loads and loads and loads of copper wire around it because copper conducts electricity. Electricity can flow through copper. And I've got a magnet here. I'm not going to do it right now because I will have current flowing through my copper wire when I attach the battery and it's going to get hot. So for the moment, I won't attach it. What mistake have I made? What mistake have I made? Why isn't this the bestest electromagnet you've ever seen? There are loads of reasons. But I've got copper wire. I've wrapped it around a steel chisel. I've got a battery that I can, okay, it's a cell, that I can attach to the wire. What have I done wrong? What mistake have I made? Straight away. So hopefully you are all shouting at the screen. I used a steel chisel. Okay, why is that a problem though? You've always got to say why, haven't you? Oh, it's not IGCSE. I've used a steel for the core. So the reason that's a problem is you could say it means my electromagnet will probably stay magnetic when I turn off the electricity supply. Or you could say I won't be able to turn the electromagnet off. Or you could have said the opposite. You could have said if you using steel isn't good because iron is easily demagnetized. You should use iron instead because that will demagnetize more easily and you'll be able to turn the electromagnet off. Something like that. Okay. I will prove to you now that my electromagnet does work, okay? So there's my coils of wire. Just move them up a bit. This is a bit fiddly because I'm holding my phone with my other hand, but I am going to attach the battery now, but not do it for too long. And I'm going to see if my electromagnet will pick up this magnet here. So the wonderful Katie, whose dad works at CERN, sent me these gorgeous, gorgeous magnets. So I'm going to see if my electromagnet will pick up this magnet. You ready? I'm going to attach the battery. There we go. Okay. Ready? 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 Oh, come on! Guys! So if you're trying this at home, be really careful because the wire will get hot. No way! I picked it up! How good is that? How good is that? How good is that? How good is it? That's your next question, basically. I use my magnet to pick up a magnet. It works. What second mistake have I made? I know. some of you might not be getting this, and some of you will be really obvious. Well, what mistake have I made? It's a magnet, isn't it? And it's steel. It's a steel chisel. It's a steel chisel, and steel is a magnetic material. So steel is attracted to magnets. Like, there's no battery connected here. All I've proved is that steel is attracted to magnets, which we knew anyway. We don't need this to be an electric. You get me, don't you? Right. The other thing, I'm going to give you a moment to think about it, but it's very difficult, and I don't think you'll get it. But it's something else I would have to check. Like, if you really got a piece of iron, and you say you were like working in your garage, you grabbed a bit of iron, you got some copper wire, you wrapped it loads of times, really bunched together, you got a really strong battery, and you connected it in a way that was safe to the wire. What would you also have to check for? Right, while you're thinking, I'm just going to cut out another little lollipop, and then we'll put a hole in it. What's another thing that I would have to think about? It's not obvious. They might ask you this. Certainly, when I've been knocking around at home trying to make electromagnets, this has come up for me. So I'm putting my current lollipop on top of another little bit of cardboard and just cutting out another one. It's something to do with the electric current. What I would need to make sure is that my copper wire was insulated. Insulated means it's like a little bit of plastic wrapped around it. I mean, all of the cables that you can see in your house will be insulated, because you don't want just electricity flowing through exposed wires in your house, do you? So all of your computer charging stuff in your house, it's all got like rubber wrapped around it. You need to make sure that the electromagnet has that, because if this is just copper wire touching steel, when I attach the battery, the turns become completely pointless, don't they? I've tried to put as many turns on my electromagnet as I can, so that I get loads of charge there, so that I get a strong magnetic field. But if the current is just like bypassing the wire and flowing through the core, flowing through the iron core, then there's actually not really very much current flowing there, because, well, if you do the electricity lessons, the resistance isn't very high. It's just, yeah, it wouldn't work. So I don't know, they might test you on that. So just for the sake of completeness, I've written at the bottom, what third mistake might I have made? Is my wire insulated? Should it be? Brackets, yes, it should. Right. How have you got on with your potential egg whisk? So this is the tricky bit. I really mean this. It sounds patronising, but it's quite hard to cut holes into cardboard without hurting your fingers. What you need is to cut out a hole so that you have, why am I trying to draw it? I've already got a practice one I can show you. You're trying to cut out a hole like that. So, I mean, it's hard to do. You've got to kind of curl it slightly and then slice into the middle, but keep your hands well out of the way. It's all right once you've got one cut, isn't it? Because you can just stick the scissors in and move it around. But do be careful, please, friends. I don't want, because of you, I don't want anyone losing fingers, but I also don't want to be sued. Because you had some sort of terrible cardboard egg whisk related injury on my watch, okay? There should be an adult in the room with you anyway. Right, so I've cut out one of those, and I'm going to do the other one while we're chatting, okay? So you should have something that looks a bit like that. I'm still not entirely convinced this is going to help you understanding, but it's too late now. Okay, do you remember last week we talked about the right hand grip rule? Oh, it was ages ago. Do you remember? We were using our right hands to make a loose thumbs up shape. And I showed you this diagram, and a lot of people got quite stressed out about it. It's the thumb shows the direction of the magnetic field, and the fingers show the direction that the current is flowing in, or it could be vice versa. Well, what I'd like you to do is erase that from your mind. Get rid of it. Not forever, but put it in a very well sealed box. You might need it if you ever do an IGCSE exam. But today we're learning about the left hand rule. Yeah. Okay. So I know. Right hand rule, grip, electromagnets, just park it. Put it somewhere where you need a ladder to reach it, okay? And while I'm talking to you right now, please be cutting out your other egg whisk. So you've got two little egg beater things. So yeah, there's this fact, which I've taught some of you before, and it's a massive deal, and it is used so much in everyday life by humans this really weird natural phenomenon that the universe has just given us. And the way that it gets talked about in physics, it sort of makes it feel quite boring. I've put an exclamation mark on the end to try and jazz this sentence up a bit. A conductor, like a wire, something that allows electricity to flow through it, right? Something that lets electricity flow through it is a conductor. A conductor, like a wire, with a current flowing through it, experiences a force when it's placed in a magnetic field. Does that sentence make any sense to you? It's an incredible thing that happens. A conductor like a wire with a current flowing through it experiences a force when it's placed in a magnetic field. I've employed Theatre of Science mascot Billy the Liver to try and put this in more friendly language for us. Here's Billy the Liver saying, picture something with electricity flowing through it, right? If you put it near a magnet, it moves. OMG. Now, obviously this is, like, we can demonstrate right now, this is not true. You must be thinking I'm talking absolute nonsense because I've got a wire here with current flowing through it and I've got a magnet and look, there's nothing. It's not working, is it? But it can work. This is an incredible phenomenon that actually really does work. And if you've got a motor with you, it's how motors work. So we need to talk about it. You'll be pleased to hear. So you know how magnetic fields have a direction, right? We talked about this. Oh, how have you got on with these two little egg beaters? Have you done them? Can we move on? I don't want to go too quickly. Hopefully you've done them. When you've done them, on one of them, can you put a slit halfway up the lollipop stick going upwards and a slit going downwards into it at the top, but don't cut into it, don't actually cut into the hollow bit in the middle. It's easier to show you what I mean, isn't it? What we need to do is we need to cut little slits so that we can actually put them together like this, like I did yesterday, and it worked really well. So I'm feeling a bit nervous because the odds of this working twice. But here's what I did. In one of them, I cut up the lollipop stick like that and cut about halfway into the top. Okay, so can you do that as well? I'll do it online here. Cut halfway up the lollipop stick and then cut from the top. So you're always cutting from the outside, but just cut halfway. Oh, it's quite hard to do without cutting into it, but I've done it. I'll try and show you there. There you go. So just a little cut at the top. You can always do more. Stop it, Laura, stop it. And a bit at the bottom as well. So yeah, we've talked a lot, hopefully, about how magnetic fields have a direction. We draw magnetic field lines as moving from the North Pole to the South Pole, okay? Current has a direction as well. If you've done the electricity lessons, we're talking about direct current. So direct current just flows in one direction. So current has a direction. The magnetic field has a direction. Obviously, if something has got a current flowing through it and it goes into a magnetic field and it moves, it's going to move in a certain direction. So we've got three things that have directions that we want to be able to talk about. If you're going to design, build, use a motor, you've got to know which way the thing is going to move. So what we use is, thanks to Alexander Fleming, we get to use a left-hand rule. This pleases me because I am actually left-handed. So you need your left hand for this. And you need to sort of pretend that you're firing a gun. Let's say it's a bubble gun, because this is a kids' show. You've got to make a bubble gun that has your thumb pointing straight upwards. You're firing with your first finger, and for physics reasons, which we need, your second finger is coming off to the side. So you've arranged your first and second finger and your thumb so that they're all pointing off in at right angles to each other, like in 3 different dimensions. Okay, I'll show you the picture. Here you go. Cool. What an incredible hand model this person was. They should be a professional. So the direction of the force, like the direction... Anyway, let's start from... I'll show you the thing that we're going to do, right? This is the sort of scenario they might show you. Here we've got the North Pole of a magnet and the South Pole of a magnet with a gap in the middle. Are you okay that you can't see it, but in between these North and South poles is going to be magnetic field lines? We talked about that in the very first lesson. Magnetic field lines run from north to the south, right? Oh, let's go down to Bath and get some, go see Stonehenge or whatever. So the magnetic field line is running from the north to the south, okay, in that direction. You've got a wire with a current with a little arrow on it showing you that the current is flowing into the screen. So they might say something like, okay, the current's going in that direction into the screen. The magnetic field lines are going from left to right. Which direction is this wire going to move in once the current starts flowing? It's a conductor, it's got electricity flowing through it, and it's in a magnetic field, so it might move. But which way is it going to move? Left, right, up, down? This is how you work that out. If you point your first finger in the direction that the magnetic field is going in, and your second finger points in the direction that the current is flowing in, then your thumb should, if you've remembered to use your left hand, and this is quite confusing, your thumb should show you the direction of the force. Is that right? That's quite confusing, right? It's especially confusing actually since I'm going to show you this and ask you what direction that wire is going to move in. But I haven't put the thumb on the screen. I'm sorry about that. I'll talk this one through with you and then you do the next one. So it has, how we remember it is first finger field. First finger field. Point in the direction of the magnetic field. Start with the magnetic field. Point in the direction of the magnetic field. Second finger current. That's the way that the current is flowing. And the thumb's going to show us the fourth. So I'm going to point in the direction of the field. Shoot in the direction of the field. First finger field. The field runs from north to the south. There we go. So I'm just pointing off to the right. My second finger now has got to point in the direction of the current, and that's into the screen. And at the moment, my finger's pointing towards you out of the screen. So I need to keep my first finger pointing in the direction of the field, but I need to twist my hand around so that now my finger's pointing in the direction of the field and the current finger is pointing in the direction of the current. Phew! I did it! So now, because these two fingers are sorted, my thumb is automatically pointing downwards, which tells me the force on this wire is acting downwards. So that wire would, in theory, if it was able to, it would move downwards. It's experiencing a pushing downward force. That's pretty amazing, isn't it? Can you have a go? Have a go with this one. So the magnetic field is facing in the same way, but now the wire is moving out of the page. Which direction is that wire going to want to move in? Which way is that pushing force happening in? So first finger field, point with your finger in the direction of the field. Second finger current. Make sure you're using your left hand. What you should find, if you point in the direction of the field, your second finger current is, well, mine's already coming out and pointing at you, just like that wire, so that's right. And my thumb's pointing upwards. Yay! So this wire would be experiencing a force in the upwards direction. Okay. Let's finish off our egg beater very quickly, and then I'll give you some questions to see if you've understood that. So one of my egg beaters I've cut in from the top just a little bit, halfway, and I've cut up from the bottom along the stick. I need to do the opposite on the other one. So on this one, I need to cut in from the inside both times. Start on the inside and cut halfway up, and start from the inside at the bottom and cut halfway down. Do you see what I mean? So this one is done now. I need to start on the inside and cut upwards like that, but not all the way. and at the bottom, I need to cut downwards about halfway as well. I cannot emphasize enough how this is all about learning and understanding and not about making a really great motor. Mine are all going in the recycling bin after this, but it won't hurt. I don't think it'll hurt your understanding. There you go. So you've got one that's got a cut up the stick and down from the top, and you've got one that's got a cut. You start off in the hollow in the middle and you cut upwards a bit, and you start off in the hollow in the middle and you cut downwards a bit, okay? Right, I've got some questions for you. I've got some arrangements of magnets and wires. If you have been to my website and you've got the free printouts for this lesson, then you've got it in front of you and you can just draw a little arrow. Otherwise, just do what I'm going to do and do it on some paper. Yeah, here you go. If you're ahead, you could try and get your egg beater together. You could even, if you're feeling very brave, there's an adult with you who can do things like stab a hole in a box, get an adult to do it, right? It's tricky, this, but I'm going to cut a hole in the side of my box and start putting my egg beater together, but I will show you how to do it in a minute. Right, here we go. Let's have a go at this. Super difficult because, yeah, I haven't put the left-hand rule on the screen for you. So remember, it's your left hand, everything's at right angles to each other, and first finger field, you're pointing in the direction of the field, second finger current. The thumb is the direction that the force is acting in. So the thumb is always going to give you the answer in these questions. I've put a little green dot on the wire, don't know, just try and make things clearer. So number one, you've got a magnet which is south on the left and then north on the right. Then you've got a gap and then another magnet which is south on the left and north on the right. So you've got a north and a south of a magnet with a gap in the middle, and there's a wire in the middle with the current flowing into the screen. So can you tell me which direction that wire would move? Up, down, left, right. Number two, it's the same except the magnets have swapped over. So now the south is on the left and the north is on the right, with a gap in the middle and the current still flowing into the screen. Question number three, this time the magnets are on top of each other with a gap in the middle. So you've got a north pole and a south pole, and then a gap, and then underneath a north pole and a south pole. And in the gap you've got a wire with the current flowing from left to right. Number four is exactly the same as number three, except the top magnet has been switched. So now you've got two north poles facing each other and a wire carrying the current from left to right. And number five is the same setup as number two, south pole on the left, north pole on the right, except this time the wire is flowing from the north pole towards the south pole. So it's parallel with the magnetic field. And you've also got two more wires on top of each of the magnets as well, like parallel to the magnetic field. Right, while you're doing that, I'm going to try and stab a hole in the side of this box. It went up a bit late because my, I think quite appropriately, my Lego story show about Tolkien ran on a bit. But on my Facebook page now, if you're watching live, is a post where I always say, if you would like to comment on this lesson, then you can go over to my Facebook page, leave a comment, and I will read it at the end. It's always lovely to hear from you. So yeah, if you haven't got a Facebook page, don't worry about it. Like I always say, it's kind of the right answer. Facebook, not a notoriously lovely, ethical company. But if you have got one, feel free to go over there and use it. Say hi to me. On the top of my page, Theatre of Science is a post. And yeah, I'll have a look at it at the end, see if any of you have left me any comments. Okay, I have made a hole in the side of my box that I'm going to poke my egg beater through in a bit. How are you getting on? If you're confused, that's probably the right answer. Some of these will not work. I know, right? Yeah, some of them won't work. I'm sorry. Okay, I'll give you the answer to the first one. We just did it really, didn't we? So number one, what have we got? Point in the direction of the field, from north to the south. Oh, the houses are more expensive, but all the museums are free. So point from the north to the south, first finger with your first finger field, okay? The current, second finger current, is going into the screen. So I have to turn my hand around. My first finger's pointing in the direction of the field now. The current is pointing into the screen, so my thumb is showing where the force would be acting, and it's downwards. So downwards. What's the answer to number one? The temptation is to swap your hands, isn't it, to make it easy, but that's not how this works. It's got to be your left hand. So I'll do the second one. So the second one, this time the magnetic fields have swapped over. So this is very awkward because I've got to use my left hand still. So you go from north to south, pointing the direction of the field. From north to the south. Oh yeah, let's go and see Wicked. And stay the night in a hostel. So we point that way, first finger field. My finger is just automatically going into the screen, which is correct. And my thumb is pointing upwards. Ugh. So the answer to number two is upwards. Yay. Number three. Oof, what's happening there? So my first finger is going to point in the direction of the field, north to south, so upwards. The current is flowing from left to right. So if I do that, I end up pointing my thumb at myself like this. Is that okay? First finger field from the north to the south, second finger current going off in that direction to the right. So my thumb ends up sticking right out at me. Quite hard to draw that, isn't it? If you were writing that in an exam, you would say out of the page. I mean, it's out of the screen, but if you're doing an exam, as I write, it would be, it's coming out of the page towards you. Did you get that you can't do number 4? You can't do number 4, can you? Because this isn't a parallel magnetic field. There are not straight magnetic field lines flowing between these two magnets because they're both north poles. So the field lines would be going away from each other. So you just can't do that one for that reason. And number 5, sorry, that was also a mean trick question, because we do have magnetic fields here in between the north and south poles, but they're parallel with the direction of the current. And that's not what Fleming's left-hand rule is. In fact, Fleming's left-hand rule sort of tells us that a force wouldn't be experienced in that situation, because that's just not how it works. Things have got to be at angles. So yeah, if you couldn't work it out, well done. You were kind of right. Number 5 does not work. Okay, so why is this actually useful? Why is this idea that if you have wire between magnetic fields, why is that a good thing? Well, let's put our egg beater together and see if it helps us learn, okay? So if you've got the one with the bottom slit, try and put it inside the one with the top slit, and see if this works. I've gone small today, it's a bit more flimsy, but I don't hate it. And then hopefully you should be able to get the top bits to join up as well. That's not too shabby. It's a little bit curly, but I'd rather that than it broke. So I'm going to take that. There we go. I've got my little egg beater thing. What you've actually made, if you've managed to do this, what we're going to say that it is, and we've done it, I mean, it would be quite a learning process for you to just say why this is a horrible, horrible model. This is all supposed to be wire. What we've done is made it look like the wires all crossed over with each other. These 2 egg beaters are supposed to be completely separate bits of wire. They're not actually supposed to be attached to each other. It's amazing actually how, for me, I think I've understood motors, and as soon as I come to build a model, it makes you go, wait, what's happening in the top there? Like, how does that work? So for me, this was actually quite useful. This is not wire that is connected together. It's 2 separate bits of wire. So if you've got your box, can you draw a big N on one side and a big S on the other side? Because what this is 2 magnets facing each other. Okay, let's put it in here. I'll do a north and a south. It doesn't matter which side you do. We need to make one extra little thing, really. What you need to make is this thing. You need to make cut out a little cross with very long, thin arms and shorter, wide arms. See what I mean? Like that. Like a little creature giving you a hug. Shall I stick it on the board so you can kind of see what I'm talking about? So you've got wires that are sort of in an egg beater shape. I'll just cut one out in front of you with the rest of this cardboard here. Wires that are an egg beater shape, and they've got to have current flowing through them. So what I'm very quickly making is some long wires, and the big bod. It's not very long actually, is it? Oh well, it's for learning. This is not going to be a craft which spends the rest of my career sitting proudly on the shelf behind me. I'm sorry, electric motor, it's just not. I'm going to point you towards a YouTube video after this, which explains beautifully how electric motors work, so you can have your really shonky cardboard version in front of you. What I want you to do is to curve the big bits over, so you've got sort of like this little box, and then curl the thin arms up. So you end up with sort of like a box with horns. See what I mean? Is that okay? Right. What is an electric motor? Well, I'm just going to hold that there because that was quite fast. The principles of an electric motor are, if you imagine that one of your egg beaters is a wire, I'm hoping that you can listen and cut at the same time. Sorry. You've made wide bits, narrow bits. The wide bits get folded over like that. You've got this egg beater, which is actually a wire. So electricity flows through the handle of the wire, along the kind of egg whisk bit, down the other side, and down back out of the wire again. If it's wire and it's got a current flowing through it, if we stick that bit of wire, that egg beater, in a magnetic field, it's going to experience a force. Yeah, this is very, very basically what a motor is. So if you've crafted something a bit like this. What we're going to do is get our egg beater and stick it in the hole that we've made on the side of our box, in between our magnets. Oh, okay, starting to make some sense now. Now we've got wires with electricity flowing through them between two big magnets. Okay, so this is the important bit, chums. Have a look at my very shonky model of an electric motor with me and see if see if this helps it make sense. Here we go. Get my pen as well. Trying to point the bits upwards that don't have breadstick pictures on so that you can see more clearly. Right. Should I just... No, I'm not going to show you a picture of a motor yet because I think it might scare you. It's quite confusing. What this bit was supposed to be is this big bit here is supposed to be a battery. I'll label it just so that you don't forget. This is a battery. And coming out of the battery, we've got wires here. So these are wires. These bits of the wire are actually brushes for reasons which I will explain. Wow, that says brushes, okay? That's what brushes looks like when you write it while you're also holding a camera phone. So we've got battery. We've got some brushes. My battery is a bit too high. I'm just going to snip some bits off. Those brushes have to just brush against the electric whisk wires that we've made here. Here we go. So what I want to do is to fold up these little brushes so they're just touching this wire here. I don't think I'm going to be able to do it, but I'm going to attempt to do it very vaguely, just so you kind of get the idea. So they should really just be touching that. Could be worse. Let's cut that one down a bit. Cut that one off a bit. Here we go. That'll be fine. So if you imagine that these little brushes have got electricity flowing through them from the battery, what happens? Let's have a look. Let's do the proper learning bit. So let's say that electric current flows through this brush. This brush is touching this bit of wire. So current flows through the brush, through this bit of wire, all the way along there in that direction. That's important. Shall I draw that arrow on? So the current's flowing in that direction. There we go. Going around this corner, coming back in this direction. Can you see what's happening? You're starting to get it? And then it comes back out through here, touches that brush and goes back to the battery, okay? So if these brushes were touching this little bit of wire, then we'd have a complete circuit there. Electricity flows through that brush, through that bit of wire, all the way along there, all the way down there, and all the way back down there. What does this mean for us now that we've learned about the forces acting on a wire, okay? Let's have a look here. Let's get our left hand out and see what is happening. So here we've got, God, I wish I'd put these in the other direction. We've got a north pole on the right and a south pole on the left. Oh, so I need to point in the direction of the field. First finger field, current field lines go from the north to the south, so I need to pull my left hand around like that. Which way is that current flowing? My second finger's already lined up. The current in this wire here, on the left, is flowing in that direction. So I've got my thumb up now. So there's a force on that bit of wire in the upwards direction. Let's see what happens when the current kind of comes around this corner and back again. Well, point in the direction of the field. So off to the left, north to south. Second finger current, holy smokes, how, oh, ow. I've got to turn my finger so that the current flows in the direction of that way, and now my thumb's pointing downwards. So we've got an upwards force on this bit of wire and a downwards force on this bit of wire. What does that mean? Oh, finally we got here, chums. It means, did I say upwards on that side, downwards on that side? It means it's going to turn, isn't it? Whew. Now, what could happen, it would be unlikely to happen because of the momentum, but what could happen is we could have that wire respond to its turning force, but end up sort of like that, facing that way, and the thing could stop moving. So what you do is you get another piece, because now look, there's like, you've got a downwards force, but the thing's sort of acting directly over the thing, if you know what I mean. Like, there's no turning force there. Do you get me? There's still a force acting on those wires in the middle, but because it's both in the same direction, it's not turning. But now you've got these wires, because they've just moved into the right position again. Whew. So the turning force continues and continues and continues and continues. Are you ready to see the actual diagram of what it actually looks like? Thank goodness to this person putting this on Wikipedia. There's a few things that we've missed out. So that loop of wire, your bit of egg beater, is more correctly called the armature. But that is basically what an electric motor is. The big important bit that we missed out is the bit called the split ring commutator. What I need you to do now, it's not even a request. What I need you to do, now you have this quite shonky little cardboard model in front of you, is you don't need to do it right now, but you need to open the tab now so that you've got it ready for when you can watch it. Maybe have a bit of a screen break, and then look up on YouTube Jared Owen and his, what do you call it, like a animation of how an electric motor works. His explanation of how an electric motor works is beautiful. What am I even writing on the board? Electric motor. Look up Jared Owen electric motor. It's fabulous. But the problem with YouTube videos is obviously you can't like take the thing and move it around and sort of inspect it. So as much as this is like, definitely physics teachers will be tutting at me for this. I feel like if you're watching that animation that he has done and you've got this thing in front of you and you can start to piece together like why this isn't quite right, but you can also move it around and look at it, I think that's going to hurt. It's not going to hurt what we've done today. I think Jared Owen's video, along with what we've done today, might suddenly help it all to click into place in your head. But yeah, that is what an electric motor is. If you brought an electric motor with you, then you might be like me and you can look inside one. If you didn't bring one with you, don't worry about it. Look, I've got one here. So can you see that this is the more usual shape of the magnets? That's a magnet, that curvy bit there, and on the other side as well. And all that copper wire, like you don't usually just have one bit of copper wire. That copper wire, obviously you want as much charge in there as possible, because that increases the force. So yeah, lots of armatures in there. The egg beater that we've been calling it. Nice curved magnet. Yeah, that's an electric motor. Makes stuff go round and round. You've probably got them all over your house and never really thought about it if you've got an electric fan or a bubble gun or a billion other things. Right, you lot. That is the end of my IGCSE physics lesson about electric motors. I hope that you enjoyed it. The first time I taught that lesson, I didn't bother doing the craft, but I enjoyed it this time actually. It didn't confuse me. It didn't not help my understanding. So thank you for doing that alongside me if you did. Right, I'm going to go over to my Facebook page and just see if anyone has left me any comments on my Facebook page on this message that got flung up at quite short notice. But some of you, you're very good. Some of you always go to Facebook so that I do not feel too lonely. And some of you always lurk without saying hi to me on Facebook, which I also really appreciate because I always say, if you all commented, then this would just take forever, wouldn't it? It would be impossible to manage. So you're all doing the right thing. If you just watch on YouTube and like and subscribe, then that's great. And if you're going over to my Facebook page, comment, that is great as well. You can pay me for these lessons. That is how this works. It's so weird. We just fell into it by accident during lockdown. I started teaching for free. The home ed community started watching and we just really got on, right? So everything that I do is free. I'm trained to teach physics. I stream these all ages physics lessons into the internet. Well, IGCSE physics, you can do them at any age. I also happen to have a drama degree and quite a lot of performing experience. So I use that as well. I do an all ages Lego story show every week and I do all ages lessons. The printouts for the lessons are free. And I just say, if you can afford £5 a month towards all the work that I'm putting in, please can you support me on Coffee? Thank you so much. And you just are. It's incredible. I never would have planned it like this, but you are. So this is my job now. I will send you nice things as well to say thank you. In fact, now's a very good time to sign up because you get extra nice things if you sign up now. You usually get a past issue of Theatre of Science magazine and some diffraction glasses. But if you sign up now, you get those things and you also get a little winter activity pack that I sent my supporters just before Christmas. Comments! Who's here? Hello. Oh, what are you saying? Rex. Okay, wait, Rex. We better go to everyone's comments or I'll get distracted by your interesting comment. And then I might forget to click all comments. Here we go. All right, cool. Rex, I've got cylinder magnets and put them together side by side. But then when I put them on top of a big magnet, they snapped to go on top of each other. Oh, interesting. I've got cylinder magnets and I put them together side by side. When I put them on top of a big magnet, they snap to go on top of each other. Oh, that's very interesting, isn't it? So you've got magnetic fields. I don't know. Is it that the big magnet is winning? So they've both like jumped to be in line with the... Yeah. I'm trying to think how that would work. Like how it would work that the poles would line up. They must have lined up with the poles of the big magnet, I guess. Hello, Freya. Hannah's off reading a book. Ah, that's nice. Freya and I, Mum, was stressed out about you testing the electromagnet by picking up a magnet and found it funny when it turned out to be a deliberate mistake. Oh, good. Yeah, I feel like maybe I spent too long going, wow, look, guys, it works, and would have really annoyed you. Yeah, no. Yeah, someone else going like, yeah, that got to us. Hello, Jacob. Hello. Hello, Laurie. All right, Kai. Hello, Orla and Bastian. Do all motors use magnets? That's a great question. Do all motors use magnets? As far as I know, and I have to admit, this is where we get to the bit where I haven't done a lot of work on this, like outside the syllabus. And this is why this job is great for me, because when I first trained as a physics teacher, I literally just learned the things that were on the syllabus, like what you need to know to pass the exam. And the more I do this job, the more I start actually researching and find out that some of the stuff that you say to pass the exam isn't actually quite true. As far as I know, like the motor effect is about how charged particles like electric fields and magnetic fields interact with each other. So if it's a motor utilising the motor effect, then it would have magnets, yeah. Someone was talking the other day about, oh, is it okay to use a motor with like that's part of a wind-up toy? If you've done the forces lesson, you know that, I don't think you would call that, that's like a clockwork, which is slightly different, something that winds up, which uses like elastic energy. I wouldn't call that a motor. Like you don't get a motor in a watch, right? But I don't know if that's what you meant. All right, Alfred, that's a great question. Alfred, sorry that I was stressing you out too much. Hello, Jacob, thank you for your picture of a cat. All right, let's do a little refresh just to make sure. I really want to see your magnets now, like popped on top of each other. That sounds like it would be quite a good theatre of science activity. Oh, gasp, there has been a new comment. Let's see. And then I'll go and start planning for next week, actually. There's Jacob and Laurie and Kai and Orla. Orla, oh no, you'd said that comment already, hadn't you? I think so. Maybe I hadn't said hi to Orla. Orla, I'll say hi to you again anyway. I felt like I had. And there's Kai. All right, cool. Well, Facebook is telling me that is everybody. So I'm going to go. Thank you so much for joining me. Thank you so much for your actual cash money. I keep threatening to, and then I keep not updating the homework PDF that used to go with these lessons. I think I should do that because this one is a particularly good one for like other resources that will help your understanding. So I really will try and do that. I will see a lot of you on YouTube tomorrow. Big YouTube day tomorrow. We've got the YouTube version of my Lego lesson about sort of colours and dye, the YouTube version of my Tolkien lesson, or like show, and the YouTube version of my friend Tempest's English lesson about Greek myths, about Atalanta, not Atlanta. Two different things. Learn that today. Thanks, Tempest. So I might see some of you on YouTube tomorrow. If not, have a lovely, lovely week, and I'll see you next week. Bye!